So we start with where we left last time. We had an expression for the input signal power as v square by 3 and an expression for the quantization noise power as del square by 12, delta being the step size, okay, and hence the signal to quantization noise power ratio, both are power parameters, and hence S by NQ is a dimensionless quantity, came out to be very simply as m square, where m is the number of quantization levels. Okay. So Si by Nq is equal to m square. That's what we arrived. We found last time, and it was very simple to see that to have a larger signal to quantization noise ratio, which is a desirable thing, one has to increase the number of quantization levels. Okay. Now let me define S naught or SO as the quantizer output signal power. Okay, and then we can fairly assume that the quantizer output, which is very similar to the input signal, except that the amplitude has been quantized to the nearest allowed level, we can assume that the output signal power is more or less the same as that of Si, because in some cases the amplitude will be reduced a little bit if the actual signal amplitude is a bit higher than the nearest allowed level, and in some cases, in the equal number of cases, I can say the signal amplitude will also be enhanced after quantization when the actual signal amplitude is a bit less than the next higher allowed threshold that way. So that way sometimes the signal amplitude will appear higher, sometimes lower compared to the actual signal amplitude, and this will occur with equal probability. Okay, and hence we can say that there is no apparent loss in the signal power at the output of the quantizer, and hence this assumption is a fair one. Output is almost equal to Si. Okay, especially when delta is small, etc. Smooth filtering is an essential part really of getting back the corresponding analog signal from the quantized output. So S naught by NQ again is approximately equal to m square, and which now bringing in that parameter n, the number of bits to be used for representing each sample after quantization, we can find that S naught by NQ is 4 to the power n, okay, numerically, and then this kind of ratio of signal and noise power, as you know, we usually express in dB, decibel, isn't it? So in dB, signal to quantization noise ratio, where the signal power as if is being assessed at the output of the quantizer and the quantization noise power is also being assessed at the output of the quantizer, this ratio in dB then comes out to be 6.02 n or approximately 6 n. Is it simple to remember? Okay. So tell me quickly, though this analysis is not valid for speech signal as we have noted earlier, because speech does not have uniform distribution, still just to have a quick comparison, for an 8-bit QP, 8-bit PCM coded speech signal at 64 kilobits per second, for that kind of speech signal, how much is the approximate signal to quantization noise ratio? 48 dB approximately. Okay. Actually, we will take it up later on, maybe in a tutorial class or elsewhere. The actual signal to quantization noise ratio for speech signal 58. How do you know that? It's not 58 really, it's less than that. It's less than 6n basically. It's less by about 7 dB. Okay, it's around 41, 42 dB with 8 bit. Okay. Anyway, we'll take up this example later on. For the time being, it's let it be simple to remember that if the signal is uniformly distributed within plus minus v, okay, and n bits are spent for some, representing one sample at the quantizer output after quantization, then the approximate signal to quantization noise power ratio in dB is 6n. Okay. So this is 6.02 n dB. Okay. So just to remind you that this is acceptable for uniform distribution, okay, and if the excursion range is less than plus minus v, if it so happens that range normalization, variance normalization, as I was talking about last time, mean removal and variance normalization, if that variance normalization part is not done properly, then the signal excursion may be greater than plus minus v or maybe less than plus minus v. If it is less than plus minus v, then we can see that though there is no distortion due to clipping etc., but the effective signal to quantization noise ratio may be even less than 6 n dB. Does it make sense? I am talking about the second point, that if in a particular application the signal excursion is not up to plus minus V ever, that means that was a situation where you would like to go for variance normalization or gain adjustment. If that is not done, then the signal never reaches plus V or minus V, and as such there is no question of any clipping error etc. In that case, simply because of quantization error, we can see that the effective signal to quantization noise ratio may be even less than 6 n dB. And if the signal excursion is beyond plus minus V, that gain adjustment was necessary. If it has not been done, then we expect some clipping, okay, occasionally whenever the signal amplitude tries to go beyond plus minus V. That is a different kind of distortion we are not talking about at the moment. At the moment we are talking about only quantization noise error.
Sir, in this telephone rate speed, when we get 41 dB, that's just because we are not using the variance normalizer.
Pardon?
So in telephone rate speed, we are getting 41 dB, which is less than 6 n dB.
No, not really. That it is less than 6 dB is primarily because of a different kind of distribution for the speech signal. Okay, there is a gain adjustment circuitry which is flat really. The gain is so adjusted that the probability of clipping there is very small really, and the signal is more or less within the range usually, and for that summarily you get a gain of about 41-42 dB. Okay. Now we try to bring in the very powerful feature of non-uniform quantization. With linear or uniform quantization, we could find that we nominally get a signal to quantization noise ratio of 6 n dB. Okay, and this signal to quantization noise ratio expression was really dependent on the distribution of the input random signal samples. Okay, so would it not be very nice if we could get a quantization scheme which would not depend very much or which would be almost independent of the signal statistics or specifically the amplitude distribution. That means a desired feature for a quantizer would be that the SQNR, signal to quantization noise ratio, is almost independent of amplitude distribution. I say almost because we will see shortly that unless the signal is very well defined, okay, I mean you cannot make it totally independent of amplitude distribution. The signal is ultimately random, and when it is random, I mean it will always have some non-zero probability of having very large amplitude values etc. So, barring those issues within a certain range, almost if I can make the signal to quantization noise ratio independent of amplitude distribution, perhaps then we get a quantizer which will work with different kind of signals with different statistical parameters. Is that okay? So, towards that non-uniform quantization is a good solution. So, we can say to get this, what we have to do essentially is that we have to ensure that signal to quantization noise ratio, as I said just now, that the signal to quantization noise ratio will be less if the signal amplitude does not go up to plus minus V, isn't it? Okay. So, following this idea, we can perhaps guess that if we have a scheme wherein the signal to, and now we are expecting that signal to quantization noise ratio is independent of the amplitude of the signal value, it is independent of the amplitude distribution really. Okay. So, it perhaps means that when the signal amplitude is small, the corresponding quantization noise should be small, and when the signal amplitude is larger, the corresponding quantization noise also may be larger, so that the ratio remains more or less the same. There is a gap here. Yeah, there is a gap. What I mean to say, this is somewhat intuitive. We just now talked about average signal power divided by the average quantization noise power ratio, isn't it? SQNR, that is a ratio of two powers. One is the signal power in the numerator, the other is the quantization noise power in the denominator. These power parameters in general are some average values. Okay, we did not define anything called instantaneous signal power or instantaneous quantization noise power. Okay, So we are interested in making this average power ratio independent of the signal statistics. It roughly means that basically when the signal amplitude instantaneously, okay, for the sake of understanding, if at any moment the signal amplitude is small, the corresponding quantization error, if it is small, then perhaps our purpose is more or less satisfied. Does that make sense? Broadly speaking, when the signal sample value is smaller, the corresponding quantization error should be smaller, and when the sample value is larger, the quantization error may be even larger. Because when the signal amplitude is large, and even if I try to have a very small quantization level there, quantization error there, my signal to quantization noise ratio for large amplitude will be unnecessarily high. Whereas for the low amplitude signals, if I retain the same step size as I was doing in non-uniform quantization technique, the signal to quantization noise ratio will be lower compared to what it was for the larger amplitude signal. Does it make sense? Okay. So we say that the quantization noise or quantization error, okay, should be related to the amplitude of the signal. When the amplitude is higher, the quantization error may be allowed to be higher. When the signal sample value is smaller, the corresponding quantization error should not be unnecessarily large, it should be smaller. Okay, let's proceed with this idea.
What is the gap? So you said there is a gap.
There is a gap because on the one hand we are talking about an average power ratio. The parameter is an average parameter. Okay, but to get this basic idea, now I talked about some kind of instantaneous signal amplitude, instantaneous quantization error. Okay, so you can say a robust quantizer, it should be less sensitive to signal statistics. Stating the same thing in a somewhat different manner. We say a quantizer is robust when the quantizer output parameter, the single most parameter is the signal to quantization noise ratio. Okay, this parameter, if it is insensitive to the statistics of the input signal, then we say that the quantizer is a robust one. Okay, so for that, I mean, is it not that the quantizer output transfer characteristics is going to be something like this? Sorry, x is the input to the quantizer once again, y is the corresponding output. Okay, for uniform quantizer, what we are assuming is that the quantizer output characteristics would be something like this. Let us consider up to this. Okay, and then we are having uniform step size. Now what we need is that low amplitude signal, okay, will be quantized in such a manner that the corresponding error is small, and larger amplitude signal will be quantized such that the corresponding quantization error is large. Towards that, fundamentally we need some kind of nonlinear relationship between the input and output of the quantizer. Okay, so this effect is shown indirectly here, where as if I am talking about some kind of pre-distortion of the signal itself. The input signal as if is being boosted a little bit when the amplitude is smaller compared to a linear characteristics. You can see the slope here is higher when the input signal amplitude is small. The slope is going up, the curve is going above this straight line y equal to x, and when the signal amplitude is larger, the slope subsequently is falling. That means if I consider now momentarily for the sake of understanding that I am using this kind of characteristics for reshaping the input signal, then I can say that as if the input signal when the amplitude is small is being boosted more, is being highlighted more, and when the input signal is very high, it is being suppressed a little bit. Okay, maybe I am trying to expand the signal, I mean enlarge the signal when the amplitude is small, and then when the signal is very large, I am trying to compress the signal a little bit, so that I mean its effect is considered less. Okay, and then if I do this kind of pre-distortion, that means highlight the low amplitude signal and suppress a little bit the high amplitude signal, okay, and then pass it through a linear quantizer, then do I achieve my idea to some extent? we have read about linear quantizer so far. Okay, step size is the same. What I am doing is I am boosting the low amplitude signal and I am compressing the high amplitude signal and then passing this kind of separate signal through the linear quantizer.
So when you're boosting the low amplitude signal, are you changing the amplitude itself?
Yeah, that's what I mean. Okay, yes.
But then you lose your information.
Not necessarily, because if I do this in a deterministic way, I can do the reverse operation. Okay, at the reverse operation in the decoder, PCM decoder, and can get back the original shape. But in this process of boosting and the inverse operation, what I can do is that I can, for the low amplitude signal, the quantization noise gets suppressed. Okay, and for the high amplitude signal, the quantization noise gets elongated. Really, it gets amplified a little bit, so to say. So that on an average, the signal to quantization noise ratio for low amplitude section and high amplitude section can be made more or less the same. The idea is again intuitive. We will try to give a mathematical shape to this. Okay. In practice, of course, I mean, it is not always necessary to boost the low amplitude signal and suppress the high amplitude signal. It can be done in more than one ways really. One simple way that is followed is that instead of boosting the analog signal in this manner, okay, with a different kind of gain depending on the amplitude of the signal, it is fairly easy to use a pre-designed non-uniform quantizer. Instead of using this kind of variable gain amplifier, where the signal, where the gain of the amplifier will be dependent on the amplitude of the signal, okay, and then using a linear quantizer, the actual approach that is followed in design is do this, I mean, understand this effect, analyze this effect, and then design a non-uniform quantizer, equivalent non-uniform quantizer, without any kind of gain adjusting amplifier beforehand. That is a simpler approach. Okay. So towards building such a non-uniform quantizer, we start with this concept. Okay, and we will try to then find out what should be the desired characteristics of such a non-uniform quantizer. Any question? Okay. So for the sake of simplicity in notation, I am calling this y, the relationship between the input and output, as y equal to c of x, some function of x. Okay. This kind of non-linear transfer characteristics I am calling as c of x. This is not simply y equal to x. Then what you can observe is that to get this kind of effect of smaller quantization error for small signal, larger quantization error for large signal, we can see that certain characteristics should be satisfied by this y equal to cx function. First characteristic is that this y equal to cx function is a monotonically increasing function. Whatever is the exact nature of variation, it is an increasing function monotonically. Is that okay? Okay. This kind of transfer characteristics should not be something like this. It should be increasing in nature. Okay. Then there must be an odd symmetry, okay, in the first quadrant and in the third quadrant. So this cx function I am trying to model more mathematically now. I can say that a desired characteristics of this y equal to cx function, where cx is unknown to us, we are trying to understand a desired form for cx, we can say that cx is a monotonically increasing function with odd symmetry. Okay, that is a desired condition. So c of minus x is equal to minus of cx. Okay, let this be equation number 1 for this discussion on non-uniform quantizer. Okay, so cx, the shape of cx should be such that, the form of cx should be such that c of minus x is equal to minus cx. That is one condition we will satisfy for any cx that we come out with. Second, we can also put a boundary condition. Okay, the boundary condition is that with this kind of nonlinear characteristics, ultimately sorry, because the input signal sample is bounded to plus minus v, cx also should satisfy this boundary condition, that cx function should be equal to plus v when the input signal is plus v, cx should be equal to minus v when the input signal is minus v, and when cx is equal to when x is equal to 0, cx also should be equal to 0. I said this is the boundary condition which was implicit in the previous diagram. I will get back to this diagram. Okay. This boundary condition essentially means that, I refer to the earlier diagram, that as if this was v plus v, if the corresponding point here was minus v, ultimately the Cx function should be such that it has to pass through this point, it has to pass through this point, and it has to pass through this origin. In fact, the linear quantizer was doing that. Okay, so this nonlinear function also should satisfy whatever is the function form, it must pass through these 3 points of reference. Okay, so these are the restrictions one has to put practically. So we can say that Cx is an, yes please.
So where is x being suppressed in the previous diagram? Because there's always a graph above x. Graph always goes above the
Sorry, it is a gain adjustment I talked about. You can see that the gain is related to the slope of the curve. When the signal amplitude is small, okay, the corresponding gain is y by x. Na? Del y dy dx is the corresponding gain of the signal, and that is related to the slope of the curve. Here the slope is much larger compared to the slope here. So the slope decreases when the signal amplitude is large. That means the gain value is smaller. That's why the here if the signal is amplified say by 10 times, here the signal is being amplified by 2 times or 2.5 times. So the relative gain is less here. Is that okay? So let this boundary condition be our set of equation number 2. Now we can say that it's a mathematical property that if you have a monotonically increasing or decreasing function, okay, like Cx, then C inverse x exists, and that's unique really. If you have a unique form of Cx where Cx is monotonically increasing over a certain range like plus minus v, okay, then it is always possible to find the inverse function, and this is very important for us. Why? Because ultimately being engineers we have to design the corresponding decoder there. Okay, so the inverse operation has to be applied, the inverse has to exist mathematically, and we are assured that yes, the inverse function exists because it's a monotonically increasing function. So that means that Cx times C inverse x is 1. Okay, and we by name this Cx function as a compander expression, compander function Cx, and the inverse function as the expander function. Okay, fine. Though this specific word of companding again stands for compression and expansion. Okay, we expand the low amplitude signal, we compress the high amplitude signal. So this basic operation is called as expanding operation and companding operation. But because we use both Cx and C inverse x in the decoder, PCM decoder, we say Cx function as the compander function, C inverse function as the expander function. Okay. So this is the third equation. Now let delta k be the kth step size for the kth interval. This is a major difference compared to our earlier discussion. For uniform quantization, we found that the step size delta was the same. Okay, but because we are now trying to design an equivalent non-uniform quantizer, okay, and in this process we are trying to find a desired form of Cx, we are starting saying that the step size for the kth interval is delta k. So delta 1, delta 2, delta 3, they will be different. Okay, and as you can guess, the intervals near 0 will be of smaller width compared to the intervals far off from 0, either way positive or negative. Now we write this expression. This is a an important expression really, where we can say that approximately, because we talked about y versus x curve, some nonlinear Cx function, so it is Cx versus x curve, isn't it? Now the slope of the curve I'm not talking about, which is nothing but d dx of Cx. Okay, so d dx of Cx approximately, I have to do some approximation ultimately. Okay, because I am yet to find out the curve Cx. Okay, so I am trying to find a desired form of Cx. Towards that, I am closely approximating the slope of this Cx function like this, 2v by m into 1 upon delta k. So what I am doing is I am doing two things together here. I shall get back to this diagram once again for a moment. Equation 4 there talks about the slope of this curve y equal to Cx. This curve is now y is equal to Cx. So the slope of the curve is dy dx. Okay, so dCx by dx. Now I am trying to approximate the slope of this curve. Now we can say that approximation, one form of approximation is dy dx is closely equal to del y del x, where the interval is very small tending to 0. Okay. So suppose I am talking about the kth interval, okay, and there I have a step size which is del k. I get back to this equation number 4. What I am doing is for del y, okay, I am using this expression 2v by m. I have a linear quantizer. As I said, I can use in first form this kind of nonlinear Cx function for pre-distorting the signal, and then a linear quantizer. So I am considering about the step size of the linear quantizer. What is that? Delta is 2v by m. Okay. So by this dcx dx, what I am writing is it is approximately equal to that delta for the uniform quantizer divided by delta k for this hypothetical non-uniform quantizer, where delta k may be will be of some value. Okay. So I am relating the non-uniform quantizer through this continuous y equal to cx curve and approximately writing this slope as equal to delta for the corresponding uniform quantizer and that actual step size for the non-uniform quantizer, equivalent non-uniform quantizer. The non-uniform quantizer with step size delta k in the kth interval is the equivalent one. I mean, let me perhaps quickly draw one diagram that may be good. So you have x of t as the input signal. In one form, I am saying that pre-distort how? By using y equal to cx function, a nonlinear function. Okay. Then use a uniform quantizer. You get some output. Okay. Uniform quantizer step size is delta. This I am saying is equivalent to a non-uniform quantizer whose input output characteristics will be, as I showed earlier, that I will fit the same xt. You remember the transfer characteristics for the non-uniform quantizer. My point is that sorry, if I have a pre-distorting circuit, okay, some kind of amplifier which distorts this xt signal such that it boosts the low amplitude signal and suppresses relatively the high amplitude signal, okay, like this diagram I was showing y versus x, this curve, okay, with this transfer characteristics. And then if I use a uniform quantizer, okay, I get an effect which is equivalent to as if a non-uniform quantizer, where I have as if already designed this non-uniform quantizer and passing the xt through that, and I am getting the same output here. Okay. So keeping this equivalence in mind, now what I am saying is that I am following this path now for writing equation number 4. There I am saying that I have to find a slope for this circuitry. Okay. Now this being a linear quantizer, okay, the output curve is of equal step, isn't it, as we discussed. So ideally it is y equal to x curve. Fine. So what I am doing is that I am taking this delta from here and I am bringing in the corresponding change in x over here for the kth step, and I am writing the slope of this curve as dcx by dx, like delta for the uniform quantizer divided by delta k for the non-uniform, that relationship y equal to cx there. So this is an approximation but is a good one perhaps. It's not, there is no reason why it should be very bad, and this is at least the first hand approximation, unless I have a better approximation. Okay. So this is a starting good approximation, which is somewhat easy to understand, follow really, through that equivalence of the two schemes. So dCx dx let us consider to be 2v by m into delta k, where k, the number of the number of intervals will vary from 0 to m minus 1, because there are m intervals. Any question at this point? Okay.
So why is it a ratio of the two?
Because it is approximately del cy cx by del x. Okay.
But del x is our
Del cx is the corresponding change I am expecting through the non-uniform quantizer. Okay. Okay. But for the corresponding change in the input. So what I am considering is that I am trying to find this slope really in terms of, as if I have an uniform quantizer in the first level of equivalence really. So I am considering that particular del y and del x I am taking for the non-uniform expression del x. Okay, del k as del k over there.
This will be more and more accurate as m increases.
Yeah, it will be. Okay. Now, some set of assumptions that PDF of x, the input signal, is symmetric around 0. That's fine, because we are expecting mean has been removed, as should be done. Okay. And then in each interval, let me call each interval by ik. Okay. Each interval where k varies from 0 to m minus 1, px is almost constant. We had a similar assumption earlier also for a uniform quantizer. Okay. Within an interval, the PDF does not change much. So with a similar assumption, now let us try to find again an expression for, you can guess, the mean square error, E square bar. With this kind of slope, see, this kind of approximate assumption ultimately should lead me to a possible form of Cx. Can you guess that? If I can justify this approximation and can find an expression for the signal to quantization noise ratio, I can get back to this and with a specific form of Cx really. So towards that, now what I am trying to do is that I am trying to find with this approximation what is an expression for the mean square quantization error. Then what I will do is that I will try to find again an expression for the mean signal power, which is easy to find, v square by 3. And then I will again find out the signal to quantization noise ratio for such a non-linear transfer characteristics. Okay. So towards that, I am assuming that the px, the PDF of the input signal, is symmetric around 0. Okay. Mean is removed, and then each within an interval. Now the interval is non-uniform, so I am talking about various intervals ik's. Fine. Within an interval, the PDF is more or less constant. You may argue that okay, when the signal range is signal amplitude is very high, the ik value is very large, interval is large. So is this assumption fine? I say yes, more or less okay, because the probability of such high amplitude signal usually for practical signals may be lower really. So it doesn't matter much really. So this again is a fair assumption that px within an interval is the same. Let's go forward. Now, I write yk. Yk is the kth representation level. That means the quantized output value. Yk is if an interval is defined by xk and xk plus 1, I am defining the mid value as yk. Okay. So I am calling yk as the kth representation level. It is midway between xk and xk plus 1. So it is half xk plus xk plus 1. Okay. So when xk is a sample value at the input to the quantizer, say xk is a sample value, it will be mapped to yk like that. Now, because within an interval we have assumed that the probability PDF is constant, as per that assumption we can write that PDF x, yes please.
Sir, this yk is equal to half x plus xk plus 1.
Right.
It is called only for an uniform quantizer.
No, I am using the level k. So for any interval, okay, I can find the midpoint by this expression. K may be anywhere between 0 to m minus 1.
So both xk and xk plus 1 will be mapped to yk.
Yeah, this is the interval basically. This is the kth interval. Kth interval, so the sample value will be quantized to yk.
So
you can assign it to either one really, either one. Okay. Is that okay? So xk and xk plus 1, these are the boundaries of the kth interval, so that any sample value within this interval will be mapped to yk. Is that okay? Louder please. Even
the y scale is non-uniform.
that's it, because ultimately we are talking about a non-uniform quantizer.
Because in the previous example, when you had studied about dy by dx,
Right.
then you had taken 2b by m into 1 by del k.
Del k is the step size, this difference.
2b by m is
For the linear quantizer, for the corresponding linear quantizer with the pre-distortion circuit beforehand.
xk and xk plus 1, this difference is actually on the horizontal axis. Because that is the input to the quantizer.
That's the input to the quantizer. This
Step size, that is on the y axis.
right, xk and xk plus 1 is a, I am trying to understand the kth interval for the quantizer. What does it mean? It means the range of the input signals. If the input signal is between xk and xk plus 1, then there must be one quantizer output assigned or allowed level in between this. So any signal sample value between xk and xk plus 1, if say I have a sample value here, where should I assign it to? If I have a sample value here at any instant of time, then this sample value should be assigned to the nearest allowed value at the output of the quantizer, that is after quantization. So that allowed value I am calling as yk. So this whole thing I am calling as kth interval. Kth interval is defined in terms of input signal as when the input signal is more than xk, less than or equal to xk plus 1, and hence the corresponding allowed level at its output, at the output of the quantizer, is midway between these two values of xk and xk plus 1. Is it not? Okay.
The interval size that we have on the x-axis at say any interval, kth interval, will be same as the step size of that particular like
Yeah.
say xk to x plus 1.
Right. Right.
Now xk plus 1 to xk plus 2, we have another level.
Another level, which difference will be now different.
Because that difference
Del k plus 1.
is there any relationship between the difference between xk plus 1 and yk plus 1? Xk plus 1 is xk and the difference between yk plus 1.
Yeah, because see, if I now draw another level here, so this is the kth interval. His question, is it clear? What he says is that if this is the kth interval, let me say this is the kth interval ik, and my quantization output level is yk in midway between xk and xk plus 1. His question is, if I consider the next interval ik plus 1, which is between xk plus 1 and xk plus 2, okay, then where should be this quantizer output value for this k plus 1th interval? Can anybody tell me? It's again in between xk plus 1 and xk plus 2. His question is yk and yk plus 1 they are related? I'll say yes, they are related through these boundaries of the intervals only. Okay, and as you go higher and higher, this difference between yk plus 1 and yk is also increasing there. Yes, please.
In the non-uniform sampling, sorry, quantizing, sir, you had said the step size is variable. Sir, that was step size on the output side. So what about step size on the input? I mean, the width of each.
Right. In general, both will go on increasing. Both will go on increasing. Okay, that's what is apparent if you just think a little bit on this explanation. Okay, when you ultimately talk about the equivalent non-uniform quantizer, both will change. Small x, step size along the x-axis initially will be small. The step size, the corresponding change along the y-axis will be small. Both will go on increasing. Okay, but that's in the equivalent non-uniform quantizer. Is that okay? Any other question? Then let's proceed a little bit more. So I'm trying to say that the PDF P of x Okay, P of x, PDF of x, I am approximating within an interval as P of yk. Is that okay? For the kth interval, the quantizer output level which is permissible is yk, where yk is half of xk plus 1. So I am writing the PDF as approximately P of yk as if the same within that interval, in the kth interval, and delta k, the corresponding interval size, is xk plus 1 minus xk. Okay, so I am writing equations 6 and 7 like that. Now the probability that x, the input signal, I am not writing x of t, it is assumed really, the probability that the input signal x lies in the interval ik, which is P of x really, is that probability that x is between xk and xk plus 1, okay, is, this is the PDF, please note, P of x or P of yk is the PDF, okay, and this interval has a size of del k. So the probability that the input signal will lie in that range k, the interval, is P of yk times delta k. So the probability that the input signal sample value is within xk and xk plus 1 is P of yk times delta k, isn't it?
Sir,
Yeah.
but the probability distribution of yk will be a discrete probability distribution.
Pardon? Right. So here also it is coming to that basically, because P of yk I am assuming to be constant for an interval. P of yk is something constant in the kth interval. Okay, del k is again a value, specific value. So this product is something constant basically. Okay, it doesn't vary over that interval. It has the same value really. So you can place it by 1 point. Yes. Okay, and I am giving a notation P of small k. P of small k is the probability, not the PDF, probability that the input signal is in the kth interval, and hence the corresponding quantizer output is yk. Okay, so P of k is P of yk times delta k. Okay, and as usual the sum of all these probabilities over the whole range of intervals really has to be 1. So this is an identity which would be followed really. Yeah.
Shouldn't we write yk equal to pk into del k?
Pyk is the PDF. Pyk I am writing as P of x, where P of x is a, let me go back to the earlier one, P of x is a PDF of x,
P of x is a pk.
right?
But
So
can we write it that it is okay? So px is from
within that interval,
should be P of y.
yes, that's it,
But you have written px directly equal to p.
because I am considering P of x to be constant within an interval. See, as I said,
Yes, fine. But even if it's a constant, then we should enter into the width of the interval.
that's what I am doing, delta k, no? Width of the interval is
In that p of yk is equal to p of x in that
P of yk is not the probability. See,
p of yk is the probability.
you integrate only when you find, when you are interested in finding the probability. Okay, you have a PDF expression. Okay, in this case it is either px or P of yk. Okay, now you are, when you are interested in finding the probability that the signal is within this range, you integrate, is it not? So my simple point is that this approximation was not necessary in general really. Okay, see, you have a PDF column. Now what is your question? You integrate only when you are trying to find that probability that the signal is within the kth interval. So the general expression would be integration of px dx, where x is from xk to xk plus 1. Okay, the same thing I am simplifying as in that px is constant over there. So px comes out. So it is integration of dx over xk to xk plus 1. What is that? Xk plus 1 minus xk, that is del k. So the probability that the signal is within the interval is P of yk, the constant value, times the interval del k. That's what I have written.
So that constant probability of written as pyk.
P of yk is the constant probability. So I think we stop here at equation number 8. Thank you. Please proceed.